How you doing, guys? I'm Mr. Rose, but you know that because you're in my class. And today we're going to continue talking about Newton's law, specifically about friction. So I'm not going to read everything to you. This is also going to be presented in the notes will be on Google Classroom. But we've talked about friction before. This says you've even heard it because we have talked about it. You experience friction in everyday life. Essentially, we know friction as things that slow us down. The car that hit me needed more friction. They needed to slow down faster. So friction is basically our stopping force, and I want you to try this little example. I want you to take your hand right now, I'll wait, and put it on the desk nice and light, and then move it around on the desk. So this is not my desk, obviously. Move it around. Then observe that. Now take the same hand, push down on the table or on your desk as hard as you can, and then try and slide it back and forth just as this is. That obviously is friction, and you should be able to tell that the harder you're pushing down, the greater friction is, because as we'll learn today, friction is a result of the normal force. So here we have, I shouldn't say a result of the normal force, I apologize, it's related to the normal force. Here you can see the example of, like, if you were running on socks and slid across the room, you slide, that's awesome. If you were doing the same thing with sneakers, so hopefully that doesn't happen to you, but this is obviously just an example of very slippery, not so slippery. Now, here we say friction is the evil to all motion. And the evil to all motion is because what friction does is it steals motion. It is called a non-conservative force. So friction, non-conservative, meaning we kind of just lose, in quotes, that energy. Well, what does that mean? When we rub two surfaces together, now friction is the force between two surfaces. You can't say things actually like ice is slippery. Ice is only slippery with specific materials. So you need two different surfaces. For example, if I were wearing running spikes, they're spikes. I could walk on ice pretty easily because they're spiky, as opposed to just like your regular sneakers or even ice skates or socks are another example on ice that kind of get a little bit sticky. So when there is a force between two objects, that we're going to talk about is friction. And the other thing that makes it evil is there's no definite direction. We know the force of gravity is always pointing down towards the center of the earth. The normal force in this case is straight up or perpendicular to the surface. Well, friction can change. If my motion or intended motion is this way, friction's the opposite. All of a sudden, if the police officer over here started pushing the box this way, friction will all of a sudden change and flip directions. So we can say friction is always opposite intended motion, but it's never one specific motion. Now, there are lots of different kinds of friction, and this little video is about 4 minutes. This goes through all different types of friction. There's static friction, which is the resistance of an object to start moving. In other words, an object at rest stays at rest unless you act on it by an outside force. That's static friction. Static means stationary, not moving friction. Kinetic friction or sliding friction, that's the resistance when surfaces are in motion. These are the two we're going to talk about most in class. These are the ones we're going to learn to calculate. There are other examples of friction, such as rolling friction or fluid friction. I suggest that you watch this little video. It talks all about it. But rolling friction is obviously when surfaces are rolling. Fluid friction are things like air resistance or water resistance. That's why it says liquid, that we experience in everyday life.
A world without friction.
Didn't want to play that video, but we're going to keep going. So the two kinds of friction that we're going to talk about, static friction, that's the force that must be overcome to get an object to move. So this little kid starting to pull their little sibling maybe. And then kinetic friction once they're moving. Now, I want you to think to your everyday life, what is bigger? Like, what is harder to get going? Is it harder to get something to move or keep something moving? Wait time? Good. The answer is it's harder to get something moving than to keep it moving. And we have this little graph, there we go, that shows that. What this shows is as I am pushing the frictional force, because if I'm pushing this, I push that way. Newton's third law says for every action there's an equal opposite reaction. So as I'm pushing and pushing and pushing and pushing, my force, or this kid is pulling and pulling and pulling, his force increases. The frictional force also increases. So as my applied force goes, my frictional force goes. This is whole not moving until we get to a maximum value. Once I get to a maximum value, all of a sudden it starts to move. And then kinetic friction is a solid number that's not going to change per surfaces. So kinetic friction, you can see, is lower than static friction. That means friction kinetic, moving friction, is always smaller than friction static, standing friction or stationary friction. A lot of times I will talk about this thing that is called the coefficient of friction. The coefficient of friction, I'm going to erase this, is brought to you by this letter mu. It is a Greek letter. We'll see the whole formula soon. But this mu we often call a sticky factor, or I called on the last slide, a roughness number. What that means is the higher the numbers, the stickier or the rougher or the bigger the friction between the two surfaces can be. If you notice the largest number on the whole thing, so first of all, the static number, like wood on wood, ice on ice, metal on metal, what these mean, rubber on dry concrete, what that means is like a rubber wheel on a concrete road. Those two surfaces, rubber on concrete. Notice the static numbers are always bigger than the kinetic numbers. I'm actually not quite sure that's a bad typo right there, but these are always bigger than those. 0.7, 0.5, 1, 0.8. So you should notice that. Notice thing number 2, all of my numbers are 1 or smaller, which means the largest value this sticky factor or roughness factor or the coefficient of friction can be is 1. And that's important because as we do some work, if you get a number that's bigger than 1 when we solve for these coefficients, that means you did something wrong. Now we're going to go through a couple of examples. Now, I termed this example level 1, meaning this is the easiest of the examples. So what I want to know is what happens to an object when the applied force, if in the horizontal direction, is equal to the frictional force. So what that means is if I am pushing this one or pushing it, F rhos, that's my force pulling, then there's a frictional force that's over here that I'm just going to label F. What do we know about this object? Well, it's not really a complete free body diagram, but what I can tell you is one specific thing. I can tell you that the acceleration is 0 meters per second squared. Well, how do I know that? I know that because if I remember, F net equals ma. My net force is all of the forces in the same direction. If these two things are equal, I don't need to give you any numbers. I know that if they're equal, this one minus that one, or my force plus the negative frictional force, because it's in the opposite direction, that equals 0. So my F net is 0. That means my acceleration must be 0. So that tells me one of two things. It tells me that this object is traveling at a constant velocity or that it is at rest. I cannot tell just from that. All I know is my net force is 0 and there's no acceleration. So that should have been simple math and easy to do. Call a level 2 question, and this is not scaffolded out. So I'm going to do a little work on the side. So here I have a 5 kilogram block resting on a table, and it's a horizontal surface. The coefficient of friction for static is 0.75 and for kinetic is 0.57. Now notice the static is bigger than the kinetic because static friction is bigger than kinetic friction. It's harder to get it to move than keep it moving. So my first question is, what is the minimum force needed to start this block moving? Now, I would scaffold this out, and you'll see a question scaffolded out in the very last one. And I will do that as we go. So I'm missing information here. I would actually ask a part A. But if I went right away, I'm going to throw up a whole bunch of stuff here. There we go. Now here I have Fs equals mu. There's a whole lot of stuff that's written down here. So I want to go back and remind you, you should have seen on slides before, that my friction equation is just mu times the normal force. Now, I didn't have an Fs or an Fk because this is just my general form. I could put S's for static and K for kinetic, but it's the exact same formula. I just need to know which one I'm solving for. Now, I need to know the normal force, and that wasn't given here. So how do I figure out the normal force? Well, if I look at this, I have this mu times mg. Now, this is all in one step. And as we get better at these, we might be able to do that. But I'm going to back up, and over here, I'm going to draw myself a free body diagram. So I would actually ask part A, I'm off the camera, draw your free body diagram. So I would say I have a force due to gravity going down, which we also know is the weight. I'm going to call that a W. Then I also know that I have a normal force. And I might remember that those two things on this flat plane are always going to be equal and opposite. So this very first part should be part A, calculate, I'll put it over here. There should be a hidden part A, calculate the weight of my object, which is mass times gravity. Well, if I figure out what the weight of my object is, weight is equal to 5 kilograms times 9.8 meters per second squared, because my weight is mass times gravity. I have 9.8 here. We should usually use 10. That's just out of habit. I know 5 times 9.8 on my calculator. I'll even do it for you like I can pretend. 5 times 9.8 is, oh my goodness, it's 49 newtons. Is 49 newtons. So over here, I'm going to label this 49 newtons, which means I can identify the normal force as I'm off the screen as 49 newtons. So now that I know that, I would come over here and say my frictional force static is equal to what I just figured out. Let me put the mu in, the 0.75 times my normal force of 49 newtons. Now, perhaps you see that now in one step, where this is my normal force, or my force due to gravity, multiplied by my coefficient of static friction. So that comes out to be 36.8 newtons. Now, the following question is the exact same thing. Calculate the, let me move that so you can see. Calculator, what is the frictional force on this object as it moves? So it's the exact same thing. Notice my formula is the same. Fk equals mu times Fn, except now I have a k here for kinetic friction. So my kinetic friction is mu times mg, and it's the exact same thing. Notice 5 times 9.8, that didn't change. My weight is still 49 newtons. My normal force is still 49 newtons. So now I'm just multiplying it by a different sticky factor because it's easier to move, and we get a number of 27.9 newtons. Now, if you didn't know how to do this and it was a test, you would just tell me, hey, part B, the frictional force moving is smaller than not moving, and at least you'd get some kind of points for that. Let me quick erase the board for our level 3 question. Oh, I apologize. The last one. What is the force that must be applied to keep the object moving at a constant velocity? I forgot about that. Now, we just found our moving force, that kinetic friction. Those two things need to be the same. So if I backtrack, this was 27.9 newtons. To get it moving, 27.9 newtons was my kinetic frictional force. 27.9 newtons. Those two things have to be the same. Now my net force is 0, thus it moves at a constant velocity. Forgot that I added that one. All right, now here is my level 3. Now this is a hard question. There's a lot of steps to this. Here I have Mr. Rose, that's me. I'm redecorating my new apartment because I just moved. And I'm moving, well I'm not because I got hit by a car. So my wife is pushing an 82 kilogram china cabinet across a wooden floor. It resists the motion with a force of friction of 320 newtons. On the next slide, I added that she was pushing with 500 newtons. I just forgot to put it here. So she's also pushing with a force of 500 newtons. Now, just like every problem, we want to write down these steps if necessary, right? Write down our givens, what is the unknown, write down the equation, and then solve. Now, if you need to, draw a diagram, that will help. So as I go to the next slide, it looks nearly the same. But there's my 500 newtons, and now I scaffolded this out. Draw a free body diagram. I'm going to try and put it over here so it can be there for the whole time. Now my free body diagram, I have a weight, I have a normal force, my wife is pushing with a force of 500 newtons, and it says friction is acting in the opposite direction, 320 newtons. Notice my 500 is bigger than my 320 because it's bigger than 320. That makes it easy. So there's my free body diagram that we're going to use for the rest of this problem. Part B, calculate the weight of the cabinet. I can put my marker away so we can read it because I write so well. Calculate the weight. What we're going to do is first write down my formula. My formula, whoa, that all came out too fast. My formula, weight is mass times the acceleration of gravity. Well, my weight, 82 kilograms. Remember, kilograms is a mass, not a weight, times the acceleration of gravity. We can use 10 meters per second squared. Weight is 820 newtons. That should be nice and easy. Next, I don't know why that's all coming at the same time. Identify the normal force. Notice, calculate and identify. Identify means there's no math for me to do. If I know the weight is 820 newtons, that means I must know that my normal force is 820 newtons. My next step, calculate the coefficient of kinetic friction. Now, how did I know it was kinetic friction? I knew it was kinetic friction because it was moving, and moving friction is kinetic friction. So I have to go back to that formula that we just learned. Fk, that's supposed to be a mu. Fk equals mu times Fn, which is the normal force. I now know my normal force. 320 newtons, that was given as my frictional force. I'm looking for that mu, that should be a subscript, my coefficient of friction, times my normal force, 820 newtons. Divide 320 by 820. 320 newtons by 820 newtons. Now, notice I have a newton divided by a newton, which means there are no units. My answer is just 0.039. That's a number less than 1, so I think that's pretty good. I put a box around it so I know it's a final answer. My box. There we go. I put a box around it so I know it's a final answer. We keep going. Still the exact same problem. Calculate the net force. Now, a lot of you will get stuck on this and say, oh, F net equals MA, and then try and write it down. As I write it down, hopefully one at a time. There we go. F net equals MA. And then you're going to start plugging numbers in and say, wait a second, I don't have an A. And that's my last part of the problem. That's why I have this here. Now, my net force, I know up and down my net force is 0. We already did that. 820 going down, 820 going up. But my free body diagram, 500 was F Kelsey, that's my wife, and 320 was the kinetic friction. Sorry, F wife and F friction. So it is literally just 500 minus 320 newtons. This is subbing in all my numbers. Equals 82 kilograms times A. This is the only part I care about. I can't do the last part yet. 500 minus 320, 180 newtons. And I left in the last part equals 82 kilograms times A. This is essentially the last part of my problem. Calculate the acceleration of the cabinet. Notice I put it all there again. F net equals MA. F net is what I just got. 180 newtons equals 82 kilograms times A. Divide both sides by 82. You see 180 divided by 82 is A. Thus, my acceleration is 2.2 meters per second squared. There was a lot of information here. These notes are also going to be posted on Google Classroom. This slide deck will also be posted to Google Classroom, and there will be some practice problems to go along with this. Again, for the practice problems, you need to show actual work and attempts. Mr. Rose, what does that look like? At the very least, that looks like this. I don't know how to do any of these problems. I do know how to write down given information. I do know how to write down unknowns. I do know how to write down equations. This essentially is the GUESS method. That is all I have for you. And I hope I will see y'all on Friday. Possibly with some good news. Thanks for watching.